What's up, guys? Welcome to today's show. So, let's create our own encryption cipher, shall we? I'm going to call my own cipher XSC256. And it stands for the three different processes that my cipher is built upon. And the X is for expansion. The S is for substitution. And the C is for compression. And what all this means, I will explain in much detail. And this XSC256, by the way, is the number of bits for the key. So that's the security level. And my intention is that this cipher is going to be one of the most strong in the world, basically. And I have designed it myself from scratch. And this is a symmetric stream cipher. And what that means in detail I will go into, but basically it means that you give it a key and it uses that key to produce a lot of numbers in a specific order. So if you have a different key, it will provide different numbers in a different order. And then if you want to encrypt the string hello, it's going to take the first number and encrypt the H with it, takes the second number and encrypt the E, and so on and so forth. But for now I just want to have the structure ready, and then I will show you on the blackboard how this cipher is going to work. Sounds like a plan? Alright, so let's create the XSC256.c. which is going to include XSC256.h, which I am also going to create. XSC256.h. I'm going to add pragma once, so this file cannot be included several times. And I'm going to start by defining some integers, because an encryption cipher is very centered around different numbers. So I'm going to have a type definition for, let's see here, an unsigned char, which is an int 8. I'm going to have an unsigned short int, which is a 16-bit integer. An unsigned long, I guess it becomes, but that's only on my system. I will say int instead, so it works if you're running a 64-bit system as well. So an unsigned int is the int 32, and we will have an unsigned long int, which is an int 64, but we also need to have bigger things than that. So we will have an unsigned, let's see here, I think it's an underscore big int 128, which is an int 128, and I'm also going to go even higher. Because in some occasions we're going to need 256-bit integers as well. And then I'm going to define a couple of macros for doing type definitions, but because we're going to need to do a lot of those. So we're going to have a $1, which is it's an int 8 star. And then just a couple of those as well. And this is just for convenience. So 16 means 16 bytes, which is an 128-bit number. So that's why I call them what I call them. And I'm also going to define a $I, which is a regular int, and a $C, which is a character. And finally, I'm gonna have a void star as well. Okay. One other thing that I'm going to need is a 192-bit integer. But that's not really possible to define this way, so I'm going to do a structure instead. Let's say we have a struct s int 192, and this is going to contain an int 256 x, and I'm only going to use 192 bits like this. This is going to be packed, and then I'm going to type def struct s int 192 to int 192 like this. And what is packed? Well, it means that those other bits is not filled in as padding, but we need to define what that means. So we will define packed as an attribute. Always seem to forget how this is done. Well, it's going to be 2 digits, 2 T's, I mean. Attribute. And this is just called packed like this. But it doesn't look right. Maybe I should have, maybe like this. Well, we'll see. It's something similar to this anyway. Okay. So, what else? We are going to have a main function temporarily. We're going to turn this into a library later on, but it makes things a little bit easier if we have one of those. But I will put a space in between, before it, so I know that this is a temporary thing. We're gonna have some kind of initialization function. So let's say it returns a state pointer, and it's called XSC256 init. And it's going to require a key, which is an int 256. But what is the state? We need to define that as well. So struct s state. So we're gonna have a 128-bit a data path, which I'm going to call W. maybe I'll do it this way instead. I'm gonna split it up into bytes. So we're gonna have 16 bytes of internal state. We're also going to have a list of keys, because we're going to turn that encryption key into 16 subkeys. And each of those are going to be 128-bit long. And actually, I think I'm going to do a linked list. Yeah, a circular linked list. So let's start in that end. We need a different structure for this. So let's call these let's call these round keys. So each of these will contain the actual round key. Let's say sub key here. And it's going to contain another thing, which is a int64-bit what is called a round constant, RC. And I'm going to explain all of this for you. And then we're going to have let's do it like this. So let's say we have a struct s round key. And then we type def struct s round key to round key. And now we can just say round key next. Like so. Maybe we can put those together. Okay. So this is going to be a linked list, which means that we create one of these structures and then another one, and we link them together by setting this pointer to the next structure, and the next, and the next. And the last one I will point to the first one, so it becomes a circular thing. Okay. So let's create empty things for those three functions. So we're going to have an int 192, which is the compression. Let's call it the C box, compression box. No, let's start in the other end. So let's start with the X box. That's the expansion box. It's going to take an int 128, which is the current state, and it's going to expand it to an int 192. And then we're gonna have an int 8 S box. which is going to take an int 8. And then we're going to go the other direction, so we have an int 128, which is the compression box that is going to take an int 192. And you probably don't understand much of this right now, but you will. I promise you that. And then we're going to have an f function which will just combine all of these. Maybe we can actually make our lives a little bit easier if we have an int 192. And let's call this the S boxes plural, which will just go through every byte. And then the f function, which will return, we go in with an int 128 and receive a int 128. Okay, so let's create the shells of these functions. So let's just do something like, we start with the expansion box. So we go in with the W, which is current state. And then we will do a lot of stuff here, but for now, the only thing I'll do temporarily is I'll create the int 192 W prime. Which I'll set to 0. And it with the input. And then I'll just return it. So this is the structure of the things we're going to do. The int, the S boxes will work a little bit differently. We'll go in with 192. And we will go through every byte. So let's see. It's going to be 24 bytes. Let's make this a little bit clearer by saying this is the input, this is the output. Same here. So let's create an array of 24 words, where each word is 8-bit in this case. We need to have some kind of counter. We're going to have let's see here. We want to have an output which is the same size, but we need to have some intermediate value as well. We'll do a for loop where we go from 0 to 24. At each position, we're going to set w prime equal to the s-box function of the w at position x. So we go through this 192-bit thing byte by byte. But first we need to copy the input into it. And I'm not really sure if it's possible to do it like this. But let's try. No, it's probably possible. But let's try something like this. We create a pointer. We set the pointer equal to the int 192 of the address of w. And then we set the value of that pointer to the input. If this doesn't work, we need to do a mem copy or something, but I think it might actually work. And then we go through all of them, one byte at a time. We push it through this s-box, which will return another byte. And then we want to inject that into the same array, like this. And then we should be able to set the output to the int 192 of p, and then return it. And the s-box function itself is going from an int 8 to an int 8. So I will just do this for now. And then we have the compression function. Maybe we should be consequential with this stuff. So let's see here. We need an int 192 output. Where the output is going to be the int 192 of I mean int 128 of input ANDed with, let's see, if it's 1 2 1 2 1 2 1 2, this is a 32-bit thing. So 32. So 32, 64, 128. I guess this should be possible. So I'm masking out, so I don't have all the 192 bits, I'm just taking the lower 128. And finally we're gonna have the f function, which goes from 128 to 128. So f, we have 128 input. And for now we'll do the same thing here. Just return f. No. We're gonna have an, let's do it like this. Create an output. Where the output is equal to, so first we run the Xbox of the input. Then we run the Xboxes of that. And finally we run the compression box of that. And this we return. So if this works, this should return the same value, 5. And let's make this a regular 32-bit integer. So 0x%x. This is the integer of y ANDed with 1 2 1 2 1 2 1 2. All right, let's see how many errors we have. I'm a little bit unsure about the way we handle the structure, but let's see what it says. Right, we need a make file. I will just do it very simple for now. So we're gonna have some flags. I'll set it to W all. For now, no optimizations. And I'm gonna set the standard to C23. If you don't have a new enough GCC version, set this to C23. Set this to C2X or remove it entirely if it complains. And we're gonna have some LD flags. which is nothing currently. We're going to have an XSC 256.0, which comes from C file. We're going to run cc with some flags, take the input file, produce -c input file. And when we have that, we can create our, let's call it just XSC, from XSC 256.0. And we run cc with some flags. We could take all the input files, produce an output file, and we have some possible LD flags at the end. We're gonna have an all, which is XSC. We're gonna have phony, which is clean. And the clean will just do remove all object files and XSC, like so. Let's see what happens. Yes, I mean that. The error messages are helpful sometimes. Right, I need to specify the directory for my include files. All right, let's see what we got. Big int 128. Let's do this. I wonder what I called my AES implementation. Let's check the repo instead. AESKS files. The H. Bitint. Oh, it should be bitint, not bigint. I am a little bit too influenced on JavaScript, I think. I think it's called bigint in JavaScript, so bitint. All right, let's see what we got. Okay, this is still wrong. Attribute, maybe it's only one at the beginning. Maybe it's like this. Or possibly like this. There we go. All right, so number 40, into blah, 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 Xbox. stored in the H file. Ah, that's right. And I never typedef this. So typedef struct s state to state. It's gonna have this W and it's gonna have some round keys. Let's call them subkeys here, or subkey. Incompatible types when assign it to type int 182 from type int 128. Okay, this is what I was expecting. Let's put is equal to, maybe we need to do something like this. Well, let's do output dot x instead. Let's see, what do we have here? Int 256 x. So let's cast it to int 256. Will that go? Alright, so let's do some pointer magic instead then. We're going to return an int 192. So we set p equal to the output. Let's see here. If we do this though, we might overflow the thing. So maybe we can make our lives a little bit easier by padding this thing. So we don't create some buffer overflows. It wouldn't be very secure, would it? I think it's the cast here which is the problem. All right. Okay, integer constant is too large for its type. It kinda isn't though, but I see the point. This is a 128. Cast it to a 128. Take the input. Well, maybe we don't need to worry about this. I guess if we do it like this, it will just copy the bits it can. No? Okay. Oh, we haven't declared printf. Output is uninitialized 10 in this file. Well, it kinda isn't though, because we point to it and modify it indirectly, so to speak. But if it makes the system happier, I'm gonna initialize this to 0. Incompatible types, blah blah blah, line 8. All right, it compiled. Will we get a 5? Give me 5. 5, yay! All right, so now we have some structure to this. And you probably don't understand much of this yet, but we do have the general shell, so to speak, with the different functions and so on and so forth. But now I'm gonna show you a lecture about how this cipher works. To begin with, in a high-level view. So we'll be right back after this. Alright you guys, so now I'm going to show you the high-level view of XSC 256. And it's also called Penguin 256. So the 256 is the security level, the size of the encryption key in bits. and XSC stands for the 3 different atomic operations of the cipher. It's an expansion box, it's a substitution box, and it's a compression box. And you will understand all of this when I go into the details. Alright, so first off, the cipher has 2 different phases. The first phase is the initialization phase. And that's when the encryption key is looping around and affecting the state. So we have a starting point, so to speak. And I will get into the details. And then when this is done, everything else is the key stream generation phase. And what is key stream? Well, the cipher creates a lot of different numbers in a row like this, based off of the encryption key. So if you have another encryption key that you put inside of the initialization phase, the key stream phase will produce different numbers and in different order. And these numbers, if we want to encrypt hello, for instance, then the first number is going to encrypt the H, the second number is going to encrypt the E, and so on and so forth. And if you take the same number and you try to encrypt the output with that value, you turn it back. So it's an operation which goes in either direction. Okay, so let's get into the high-level view. So we go in with an encryption key, which I will call a big K and a little e, so encryption key. So this is 256 bits. And the first thing that happens is we cut this in half. So we will have a left half with 128 bits and a right half with 128 bits. And the entire right half, that is the least significant bits, is being put into a key schedule function. Alright, welcome back you guys. I'm sorry it's a little bit shiny up here on the upper right corner. I tried to change the color of the light and dim it down a bit, so hopefully it's a little bit better. But I will try not to write so much in that corner. Anyhow, the right part of the encryption key is being sent to key scheduler. And what comes out is 16 different keys. So we have K0, K1, K2, and so on and so forth. And each of these are 128 bits. So all the way to K15. And that's the only thing that the right part of the encryption key is being used for. Anyhow, we do also have a state. So that's the internal state of the encryption. And each round, this state is modified in one way or another. And the state looks like this. So we have 16 boxes here, and these are called W0, W1, all the way up to W15. And the W stands for word, and the word length in this encryption cipher is 8 bits. So each of these contain 1 byte. And if you plus these together, you have 128 bits. So that's the internal state of the cipher. And that's where the left part of the encryption key goes. So these 128 bits is populating all these boxes inside of the internal state. Alright, so what happens next? We have something called the F function. And these 128 bits of state goes into that F function. And out comes 128 bits. So the F function is changing these bits in a couple of ways, which I will show later. But for now, remember that the state is populated by the left part of the key, and it becomes the input to the F function. And then we get 128 bits out. And now we do an XOR operation with key 0. So 128 bits of state is XORed with 128 bits of key. And then the next thing is we do a bit rotation to the right by 7 positions. And if you don't know what a bit rotation is, let's say we have 1101. And if we want to rotate this to the right, we move all of these bits 1 step to the right, and this bit right here will fall off the edge and will be moved over to the other side. So that's a bit rotation. And we do that 7 times with the internal state, 128 bits. And this right here is 1 round. And then we take the output from this and just do the next round, putting it into the F function. And this goes around like this. Until we have done 64 of these rounds. And when we have, so first we do K0, then K1, K2, all the way up to K15, and we start over with K0, K1, etc. 64 times. And then the cipher is initialized. Alright, so now when the cipher is initialized, the key stream generation phase begins. And it's almost the same. So we do the same thing. We take the internal state. So W is the internal state, the 128 bits. You know, all these 16 boxes. And same as before, we put this into the F function. And we XOR with a key. So the rounds look the same in this keystream generation phase. The only difference is we only do this twice. So this feeds back in, and then we do it one more time. So when we generate 1 byte of keystream, we do 2 rounds first. So 2 rounds, we generate 1 byte. 2 rounds, we generate 1 byte. So how do we generate these bytes? Well, we take the internal state. So let's say we have a whole lot of 1s and 0s like this. 128 of them. And the 4 1s and 0s on the right. So the least significant 4 bits. They form a number from 0 to 15. And you remember we have this state with these 16 boxes with 1 byte each. This number right here decides which one of these boxes, and each of these boxes contain 1 byte. So this becomes an index into that. So let's say these last 4 bits are like this. So 1, 1, 0, 1. So this is 1, this is 2 place, 4, so it's 5, and 1, 2, 4, 8. So 12, 13 in this case. Which means that we take the box with index 13, which is this one right here. So let's say that box contains a small a. That small a, or its ASCII representation, 8 bits, will be the first keystream generated. And then we do 2 more rounds. We generate 1 more byte of keystream, and we keep repeating that forever, or as long as we need more keystream. Alright, welcome back you guys. So now that you have a better understanding of how this thing is going to work, let's keep coding. So first I need to change some errors I did. These S boxes takes a 6-bit input, not an 8-bit. 12-bit even. So let's create a structure for that. And I can't call them hexanibbles any longer. I wonder what 12 is on Latin. Let's call them I don't know. Semi-words. That's good enough. So what does a semi-word contain? Well, it contains coordinates, basically. So it contains an X and Y and a Z with 4 bits each. So int 8 X of 4 bits, int 8 XY Z of 4 bits. And this we can make packed. And we typedef this thing. Let's do semi-word singularis. And we'll call it a semi-word. So we go in with a semi-word in the S box. And we go out with a semi-word. Like so. The rest doesn't change. Well, one thing does. Because here we are going through each word 8 bits at a time. We can't do that now. Mm, mm, mm. Let's do something like int 8 x, y, z and semi-word sw. Something like this. So we point this towards the words. Maybe we can set this pointing to the input, which means we don't need to do this. And not this. So the semi-word is going to be the S box of what exactly? Maybe we do 2 of these, one for in, one for out. So out is going to be this, but what do we give it? So when we point this towards the input, we are pointing it towards the most significant byte. Well, we need to take the 6 least significant bits from this. Okay, so let's remove this. Let's say we have an A. The A is equal to the value of P. So int 192 of P. So that's the whole thing. And this we need to AND with something. So let's see here. We need the 6 bits. So a value that looks like this: 1, 2, 3, 4, 5, 6. So this is the ones place: 2, 4, 8, 16, 32, which means that we have the 60. We need to end it with 63. That way we get the 6 bits to the right most. Let's also create another int 192 that we can keep a copy. So let's call it input prime or something, where we just set input prime to input. We point this towards the input prime instead. So now the A contains all 6 bits. Which means we can set the in dot x equal to A and this time we need to take 4 of these bits. Alright, welcome back you guys. Let's take one more go at these elusive S boxes. So let's start over here. So we're going in with an int 192. We return one of these. We have a function called sboxes, and we have an input like this. And we're gonna have some semi-words. Let's call them word. And how many are they? 192 divided by 12, so 32, I guess. Let's double check my maths. No, 16. Glad I double checked. Alright, so how are we going to do this? So we want to go through this input 12 bits at a time. So we're going to have an output of 192. So let's see here. So we need a for loop from 0 to 16. let's say we have some int16s. Let's call them in and out. Let's also have an int8 where we save the LSBs. Alright, so we're going to grab the 12 least significant bits and pass them through the sbox function. And then put the output into the output. So let's start the output at 0. And we start by grabbing the input. Let's also have a input prime that we set to input like this. So the in is going to be the input ANDed with FFF. So we grab the 12 least significant bits. Or actually, let's grab the 16-bit. So we grab all of this. So before here we have a lot of different numbers, but we're interested in this right here. So let's say we have an in prime as well. So first I want to save this part so we don't overwrite it. Let's call that the LSBs. And that is going to be the in, which are all the 16 bits. Push to the right 12 positions. And the result we're going to AND with 0x 0f. So now we have saved the least significant, let's see here, the MSBs. Okay, so we don't overwrite it. Now we want to grab the actual values. So the word at position I dot x is going to be in ANDed with 0x 0f. So these are the 4 LSBs. Then we take the y, which is going to be the in pushed 4 bits. And then we grab the 4 LSBs. And C is going to be the same, but we push it 8 bits, like so. Then we set word at I to sbox of word at I. Maybe we don't need to do it like this. We can actually do that and do this instead. So let's see here. Let's set in prime to in, and we grab all 12 bits, and we set out to our saved MSBs. We shift them back 12 positions. And we OR that with the saved ones. And now we should be able to put them back. Which means we take the input, push it left 12 bits, and then we OR it without. I think this is correct. So now I guess we just return input prime. And let's create a show function for 192-bit ints. So void show int 192. We do for loop where we set I equal to 0. We do this let's see here, 192. We go through them 32 bits at a time, so 6. We're going to point mem towards the void of the address of input plus 5. Set p equal to let's do this. Let's do +6 instead. And then we take mem and we jump 4 bytes. P is equal to the int 32 of mem. And we print a hex value with 8 digits. That is the integer of P dereferenced. Not sure if this works, but I think so. So let's make some room for the show functions. Void show int 192, int 8, and int 192. So let's see, an int 192 is 16 bytes. So I guess no, we can just do this. Address of X. Let's set it to 50 so we can see more clearly what happens. 16 bytes. Hmm, 40. 48, 49. Okay, that almost looks right. 5050. But here it looks a little bit weird. So let's try our new show function. By the way, let's create an alias because we're probably gonna have a few show functions. So a macro, that is. So let's say we have a show of X and what it does is it calls show and we add generic of X, and if we provide an int 192, we want to say int 192 of X and X, something like this. Not entirely sure, but I think so. So if I have thought about this correctly, should be able to do just show input prime. Implicit declaration of show generic. Okay, we can't do that. Maybe we need an additional parenthesis. Nope. Okay, so let's do this. We haven't defined that yet. So generic of x. Maybe we shouldn't have parentheses. Differ in signedness. That's right. This we need to cast to an int 8. Ah, look at this. Pretty nice, pretty nice. But it's backwards, isn't it? These are the MSBs, but here I'm trying to print the LSBs. Should I go the other direction, perhaps? If we just set this to input and we plus here instead. We'll go to the first memory address of the input. -4. Maybe we should push it 16 bits instead, since we're accounting for that MSB. Ah, look at this. So we add this. I think this is right. Yeah, nice. All right, so now we can successfully go through the entire thing, 12 bits at a time, and put every one of them through this sbox function, which currently is just an identity function returning the same, but it won't be later on. Okay, so the next thing is to create the key schedule, or at least the outer contours of the key schedule. And if you remember, we have this structure which is called round key, which contains a 128-bit subkey, a round constant, and a link to the next. Let's also add an identifier of 4 bits. So let's create a constructor function for one single round key structure. So it's going to return a round key pointer, make round key, and what input do we need? So we need the ID, the subkey, and the round constant. Like so. We need to have a size, a round key pointer, so the size is just the size of a struct S round key structure. And we allocate size. We assert that we have a P. Zero out that P. Then we take the PID and set to ID, and we fill in the rest of them as well. And we set the next to 0 for now. And we return P, like so. Alright, so now we can create 1. How do we do with the rest of them? So let's say we have a round key generate subkeys, let's say. And we need to have an input key. Let's also say that we have an make subkey thing. And it needs the ID. An input key. Well, basically it needs the same inputs. So let's start with the easy one. Make subkey. Then int 8 ID, int 128 subkey, int 64 RC. And for now we're not going to do much with this output. Other than return the input for now. Okay, so then we have the round key generate subkeys. And this is the key actually. This is a subkey. So first we generate the first one. By the way, we need a counter. And we need to remember the first. Actually, we don't need to pass the round constant or the ID. So the first is going to be make round key. And the ID is going to be X, which is 0. This is the first one. The sub key is going to be the encryption key. And the round constant is going to be the first in a list of round constants. So let's say we have RCs at X. And we want to create 16 of those. Like so. Actually, let's create a last as well. So first we create another round key by providing X and let's see here. And the last sub key and the RC at index X. By the way, we need to add the plus here and not here. And the last next should be P. So we make it a linked list. And at the end, we want it to be a circular list. So, by the way, so the last one next should be the first. We return the first. Let's also create a show function for 28 bits. And that's almost the same, but we only need to do this 4 times. And let's add that to our macro list. so. And this needs to be 128. Right. So let's go to our main function. Create a round key thing. And generate subkeys only takes an int 128. Make subkey. Let's see, which one did I chop down a bit? Generate subkeys only takes one. Generate subkey, yes. 8. I think this is right. So let's try generating the subkeys. Out of some value. Doesn't really matter what we put here. And let's iterate through this list. So this should be an endless loop if our circular thing works as intended. We need to create a show function for a round key structure though. So show round key. And round key. Round key. By the way, this is a void. So what do we have here? We have the ID. assert that we have a round key. And we have a round constant. And then we show the round key's subkey. And return. And let's add this to our list as well. The round key star should do show round key. Like so. All right, let's try this out. Oh, by the way, forgot to include assert. Which means we need to include assert.h and our number.h. We need to define GNU source. Show round key undeclared. What did I call it? Show round key. Expect argument of type int, but we have int 64, so 79. Okay, so this needs to be a, let's see. Is it LD? LLD? Warning, suggest parentheses around assignment. And we don't have alloc. I haven't yet decided if I'm going to use malloc or something else. So that's why I called it alloc. But for now, I will just define alloc of x to be malloc of x. And we don't have a zero function either. Let's write that real quick. Something like this should clean out the structure. Malloc, we need to include something for malloc. stdlib. Let's also add stdbool.h because we're probably going to use booleans later on. RC is undeclared, that's true. So let's say this is, we need 16 different numbers. For now, I will just do this. We can't do it like this. Alright, let's make it a global variable instead then. Something like this. We're gonna have better or round constants later on. Operation on x may be undefined. Okay. It's a little bit weird, but okay. Subkey not used. All right, let's try this out. Okay. Apparently it's a round, circular thing. But ID 4, ID. Okay, it looks right. Very good. Everything is working this far. And the show function looks pretty cool as well. It even collapsed this to the RC of subkey. All right, welcome back. So you remember we have 128 bits of internal state, and this is what we feed into the f function, like this. And if we zoom into this f function, it contains 3 different boxes, so to speak, which I'm calling the x box, the s box, and the c box. So the X box, it stands for expansion. And it means we go in with the 128 bits, we come out with 192 bits. So we increase the data path by 1/3. And that's the word expansion. Then we split these 192 bits up in something I call hexanuggets. Or maybe not. Let's call them hexanibbles. So we divide these up into, let's see how many there are. It'll be 64 6-bits. Am I counting this right? No, 32. So 32 groups of 6 bits each. And each one of these groups, so if we have one here, one here, one here, they will be individually put into this S substitution box, which is what the S stands for. So basically, if we go in with a character A, for instance, maybe we go out with a Z, and if we go in with a 5, maybe we go out with a big Q or something. So for each input, there's a predefined output. So it's a lookup table. And when all of these substitutions of 6 bits each has occurred, it will reassemble it into a 192 bit number, which is being fed into the C box, which is the compression box. And as you can imagine, the compression box compresses it down to 128 bits again. And that's the output of the f function. And then it goes back in. Alright, so here I have a drawing of how the expansion box, the X box, looks like. So on the top here we have the 16 input bytes, and we go out with 24 output. So for instance, W0 will be moved to position 4, and W1 is being moved to position 5, but it's also being copied to position 8. So every other one just moves to a different location, and every other one is copied to 2 locations. And that's how we expand from 128 to 192 bits. And here is a drawing of the S-box, the substitution box. So it's a 3D structure with 16 on the x-axis, on the y-axis, and on the z-axis. And each of these cubes contains one number, a 6-bit number. And we go in with 6 bits, so the first, we go in with 12 bits, I mean. That's right. I said the wrong thing here, sorry. So forget about these hexanibbles for now, because we divide... No? Alright, I'm sorry, I said the wrong thing a little while ago. We go in with 12 bits into the S-box, because 4 of the bits decides the x-axis, 4 of the bits the y, and 4 of the bits the z. And if you calculate this, you will find out that each number inside of these boxes will appear several times. I think they will be occurring on average 16 times each. Yeah. And that's so this is not a linear operation. We should not be able to go back. All right. So substitution is quite simple to grasp, I believe. What about the compression box? It looks like this. So at this point we have 24 bytes. And we divide these bytes up in groups of 3. And the first byte is being ANDed with the second byte, providing an output. And then we take this second byte and we OR it with byte number 3. So index 2. These two we OR together and we have the output byte number 2. And then we go along. So this is how we compress it, because each group of 3 input bytes will produce 2 output bytes. So after this operation we have a total of 16 bytes again, i.e. 128 bits. Alright, it's a lot of information in one go, but I think you will be able to understand this if you rewind a couple of times. And if you plan to code this stuff, maybe you should try to sketch it up like I have done. It will be much easier to understand that way. But okay, let's see if we can do this in code.
Very nice, very nice. But it still looks like it's in the wrong order. Because this is supposed to be the LSBs. Maybe I had it right the first time.
So let's see here, input -4. So the next position is at input +4. No, plus. I guess this should be +6. Let's see here. So we want to start one step after this thing. So that should be +16, I guess. And this should be minus, which means this should be +24. And we go minus. Okay, that looks better. All right, this is starting to take form. So let's produce the correct round constants. I want to make them out of Fibonacci numbers. So let's write the function for that. Let's say we have an int 64 Fibonacci. And if you don't know, Fibonacci is like 1 and 1 is 2. And 1 and 2 is 3. 2 and 3 are 5, and then 8, and then 13, and so on. So let's say we provide an int 64 x and an int 64 y, which are the last two numbers. And let's have an int 8 counter, so we know, no, not counter, let's say round, so we know what round we're in. So if round is equal to 0, and we return 1. Or if round is equal to 1, we also return 1. Otherwise, we return the Fibonacci of, and we provide round plus 1. And the last one is y. The new one is x plus y. And if we have all 16, so if round is equal to 15, then we will just return x plus y, I guess. Something like this. Maybe we should say maybe we should no, guess this is right. But we should probably say when we should stop. So something like this instead. So let's say we provide which round we want. With a maximum of 15. Start at round 0. Let's say we want the 4th. And we start with x0, y0. Let's see what happens. We have an int 8, we have an int 8, we have an int 64, an int 64. And we have a void Fibonacci's. Let's not delete this, by the way. Let's just comment this out. So let's see here. Let's run Fibonacci's of round 4. So 1, 1, 2. So this should be 5 then, I guess. If I did this correctly. 1. Maybe not entirely sure here, but let's start with this. 5. Huh. Would you look at that? Would you look at that? So let's go through them all. And I want to print it with a comma. And every fourth one I want to print a new line, and then a new line at the end. Something like this. I think that's right. Let's try it out. Mm-hmm. Boom. The first two doesn't look right. Maybe we should do this, perhaps. Uh, Everything works, but not the first two. But never mind, actually. But we're missing one, aren't we? 1, 2, 3, 4, 5. 1, 2, 3, 4. Maybe we should start the process with 1, 1. 2, 2. Well, let's just do this. Let's remove this. Let's change this a little bit. So we have 1, 1, 2, 3, 5. And how many are there? 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Right. Now we can delete those functions. We can put this back. And we can delete, or at least comment out this. And now it looks perfect. So it goes up to 15 with this number, then it starts over here with 1. Okay, everything we have done thus far works. And what is left? Well, basically the only thing left is creating this make sub, make sub key. So we really generate a real key, and we need the contents of the F function. So we need to create the S box, the S box, and the C box, and then we're done. But this is enough for one day. I really hope you liked this episode, how to design your own cipher and code it in C. And please don't forget to like this episode and to subscribe. And thank you for watching. Thanks for today.